let's discuss the next topic. Section 3.3, the derivative of trigonometric functions. Now, most of what we're going to cover here is actually a combination of background in trig, because we probably only need a refresher, and the derivation of the derivative of sine of x. Only a bit of it is really going to focus on the derivative of trig functions. That's toward the end. So if you're really good with your trig, then you can fast forward to the derivation of the derivative of sine of x. And if you're really, really crunched for time, then you can fast forward past that too. That said, let's review with a little bit of trig. So one thing to recall from geometry class was that if you had, let's say, a right triangle, we're going to focus on right triangles for the time being, right? If you had a right triangle, right, and maybe it's, if we zoom in a bit here, right, it's got its angles, right? This is one angle. Maybe I'll use this guy. This is one angle. That's another angle. And this, of course, is the third angle, but it's a right angle, right? It's 90 degrees, okay, right? So suppose you had that, and then suppose that you had, maybe the same triangle, but maybe you kind of stretched it out a little bit. Let me try to see if I can elongate this guy, right? You had that triangle, right? You kind of expanded it like that. Well, maybe move that up a little bit so it's in line like that. And then maybe we had, just sort of connect these two guys, right? All right, let's see if I can... Ooh, that's not nice. Okay. Really, even if I really... Oh, that's a shame. Well, let's try a little bit harder to get that looking good. There we go. Much nicer. Right? So anyway, suppose that we have these two triangles, right? The blue triangle and the black triangle. Now note that the angles in the black triangle are exactly the same as the angles on the blue triangle, right? The side lengths clearly are not the same, but the angles are the same. So we say that the black and the blue triangles are similar. They are similar triangles. Now, one thing we might remember from geometry class is that the side lengths of similar triangles are proportional. And what that means, the upshot of all that, is that if we consider an angle, let's say we call this guy theta, maybe I'll use a thin one for that, then if we consider the ratio of two of the sides, like let's say maybe this side divided by that side, given that the angle is theta, that's going to be consistent. That's going to be the same thing as, say, this side length divided by that side length. It doesn't matter how big the triangle is. It matters only what the angle theta is. So for that reason, we can define the trig functions sine, cosine, and tangent. Remember, sine of theta is, let's zoom out a little bit here. Zoom out a little bit here, right? So we'll define sine of theta to be, well, I guess if this is our angle theta right here, and if this is the side opposite of theta, and maybe this is the side adjacent to theta, and this is the hypotenuse, well, then I guess sine is defined to be the opposite length over the hypotenuse length. Similarly, we have that cosine of theta is defined to be the ratio of the adjacent length to the hypotenuse length, right? And again, it doesn't matter how big or small the triangle is. It's always the same. And then last but not least, tangent of theta is opposite over adjacent, right? Which, by the way, is the same as sine of theta over cosine of theta, if you think about it. Right? The over hypotenuses go away. There are three other trig functions that are used a little bit less frequently, but they're still important, and we're still going to list them right now. Cosecant is the ratio of the hypotenuse over the opposite, right? It's 1 over sine. Cosecant is 1 over sine. Secant is hypotenuse over adjacent, which is 1 over cosine. And cotangent is adjacent over opposite. And that's the same as 1 over tangent, or cosine over sine. Okay? you need to know these 6 functions, right? You just need to know what they are. In particular, you need to know the first 3, right? You need to totally know those like the back of your hand. But really, you should know all 6. One handy mnemonic for the first 3 is, you've probably heard, SOHCAHTOA. SOHCAHTOA. Hats off to whoever came up with that. Anyway, now that we have these trig functions, let's recall the unit circle. In fact, let's recall radians. Now, if you think about it, what are angles? Well, they're sort of measure how far along a circle we've gone, right? Like that, for example, right? Okay. Well, we're probably used to degrees. You think, well, what is a degree? What's the definition of a degree? A degree, by definition, is 1/360th of a complete circle, right? That's what it is. 360 degrees equals a complete circle. Well, okay. We could also just talk about, the circumference of the circle, right? I guess the problem with that is, well, if we're talking circumference, then we have to choose a radius. And if you're going to get technical about it, you can define radians for a circle of any radius. But for our purposes, why not just choose the circle with the easiest radius? Which in this case is a circle with radius 1. Okay? So in that case, what's the circumference of a circle with radius 1? It winds up being 2 pi, right? The circumference of a circle is 2 pi r, if r equals 1, and the circumference is just 2 pi. So for that reason, we see that 360 degrees equals 2 pi radians. And we're going to use radians in this class for several reasons. Number one, radians are dimensionless, whereas degrees are not. Right? 1 degree, you need to use a degree unit. 2 pi is just, it could be any unit. It could be, it doesn't matter what the units are, 2 pi is 2 pi, right? Also, it's just, 2 pi is just, you think of things in terms of a circle, right? You hear pi, you think of a circle, right? It just makes much more sense. 360 is a completely arbitrary number. So anyway, we're going to think of things in terms of radians, although at the beginning, we might want to think of some important angles in terms of degrees, with the understanding that we're always going to be seeing them in terms of radians. Anyway, let's think. If we have a circle of radius 1, well, then I guess we can consider the triangles, whose hypotenuses are always 1, right? Well, in particular, if we consider this triangle, I guess we can uniquely reference that triangle with this coordinate right here. Now, of course, we're on the xy axis, right? So this is the xy coordinate, right? But I guess if you think about it for a second, remember that cosine was defined to be adjacent over hypotenuse, right? And I hope we all see that this is the adjacent side length, right? However long this is, right? And that's also just by definition, right, x, right? Well, cosine is adjacent over hypotenuse, but wait a minute, the hypotenuse is 1. So the adjacent length equals cosine of this angle, theta. And that can also be thought of as the x-coordinate. And analogously, the opposite side length can be thought of as sine of theta. So really, this coordinate x comma y is really cosine of theta, sine of theta. And that's going to help us derive our unit circle. So let's get some important angles going here, right? So I'm going to have a little chart here. This is theta. This will be cosine of theta, which remember we can think of as the x-coordinate, and sine of theta, which we can think of as the y-coordinate. Okay? So first off, theta equals 0 radians, okay? Now, if we think about it, how do we know the radians to degrees ratio? Well, I guess you can just think about it as 1 degree equals pi over 180 radians, right? Just divide both sides by 360. right? So however many degrees you want, well, just multiply pi over 180 by that, right? So anyway, we're thinking about this in terms of radians, though, right? 0 radians, I think you can see that that corresponds to 0 degrees. Okay? So anyway, what's cosine of 0? Well, we're thinking about this, right? It's a triangle with, like, 0 height. Well, hold on a second. That length has radius, it's length 1, right? Because the circle is radius 1. It has no height. Right? And remember, cosine is the x-coordinate, so cosine is 1, sine is 0. Now, another important angle that we know from geometry class is 30 degrees. Right? Well, what's 30 degrees? Well, 30 times pi over 180 is going to give us pi over 6. Let me write that in blue. Pi over 6. Right? Well, if we remember from geometry class here, if we have, let me try to make that a little bit bigger here, a 30, 60, 90 triangle, where this is 30 degrees, this is 60 degrees, and then this is 90 degrees. If we're assuming that the hypotenuse has length 1, it turns out the short side has length 1/2, the longer side has length root 3 over 2. Right? That's always the ratio. So it turns out then that cosine of pi over 6 equals root 3 over 2, and sine of pi over 6 equals 1/2. All right. Analogously, this works for, I'm going to skip a space here, for 60 degrees, which is pi over 3, where sine and cosine are going to be reversed, right? Just sort of flip your triangle around, right? Now, the one in between then, that's pretty nice, is 45 degrees. Now, for that, we have a 45, 45, 90 triangle, right? Where that's a right angle, and these two angles are the same. They're both 45 degrees. It turns out that, again, if our hypotenuse is 1, that both these sides wind up having length root 2 over 2. Right? So anyway, by the way, 45 degrees, pi over 4. This winds up being root 2 over 2, root 2 over 2. And last but not least, 90 degrees. Well, what's 90 degrees? Well, again, pi over 180 times 90. Right? 90 pi over 180 winds up being pi over 2. And using a similar reasoning as before with this guy, you get 1, 0. Okay? So these are the basic angles that we have to know. Cosine of pi over 2 equals 0. Sine of pi over 3 equals root 3 over 2. Now, and do we see that these angles encompass this quadrant of the unit circle, right? By the way, if it wasn't clear, 0 starts right here, and we go counterclockwise. So then you might be saying, well, what about, like, this angle, for example? Well, it turns out it's going to behave the same way as a corresponding angle in the first quadrant. So, for example, what about 2 pi over 3? Maybe I'll use a highlighter for that. All right, what about 2 pi over 3, for example? Nah, you can't really read that, but yeah, I'll just say so what's, like, for example, what's sine of 2 pi over 3? Well, it's going to be the same as sine of pi over 3. It's just a question of whether it's going to be positive that or negative that. Well, it turns out, if you just think of the cosine as the x-axis and sine as the y-axis, everything is positive in this first quadrant. Sine, cosine, and tangent. Here, y-coordinates are positive, but x-coordinates are negative, right? So only sines are positive here. Both x and y coordinates are negative here, so only sine over cosine, tangent, is positive here. And then lastly, only the x coordinates are positive there. All right? So, for example, sine of 2 pi over 3 equals sine of pi over 3, which is 1/2. Or sorry, which is root 3 over 2. All right? Root 3 over 2. Okay? So we've got that. So that's the little trig crash course. Now, let's go ahead and derive the derivative of sine of x. We need the following fact. The limit as x approaches 0 of sine of x over x equals 1. This is not obvious, at least as far as I see it. Now, I'm going to prove this very quickly, and it's cool because it uses the squeeze theorem. Going back to our circle over here, it turns out that this length right there is tangent of theta. And theta itself, remember, is defined to be the amount of the circle that we've traversed, that the angle's traversed, right? So for that reason, we have the inequality sine of theta is less than or equal to theta, which is less than or equal to tangent of theta. Okay? Well, I guess you could think of tangent as sine over cosine, right? That's one way to put it. So if you divide all three sides by sine, then you get 1 is less than or equal to theta over sine of theta, which is less than or equal to cosine of theta. Or sorry, not cosine. 1 over cosine of theta. There you go. Now, we're really not interested in theta over sine of theta. We're interested in sine of theta over theta. Okay? So we're going to flip this. We're going to take the reciprocals of everything. Well, okay, that's going to stay the same. That's going to become that. And that's going to become that. But when you do this with inequalities, the inequalities flip. Okay? So we have that cosine of theta is less than or equal to sine of theta over theta, which is less than or equal to 1. Right? In case you're wondering, by the way, we're never dividing by a negative because we're assuming, at least for right now, that x is approaching 0 from the right. You can do a similar sort of proof for x is approaching 0 from the left. Just an FYI. All right, anyway, since the limit as theta approaches 0 of cosine of theta equals 1, right, because we just showed that cosine of 0 equals 1, and it equals the limit as theta approaches 0 of 1, by the squeeze theorem, the limit as, I guess it's theta approaches 0 of sine of theta over theta equals 1. And yeah, you could use x's if you want, but we're using angles, so I say theta. All right, so great. We have that result. Now we're going to show that the derivative of sine of x is cosine of x. Very, very nice result. So let's do it. How are we going to do this? Well, we're just going to use the limit of definition of the derivative, right? Really no other way to do this, okay? So the limit as h approaches 0 of sine of x plus h minus sine of x all over h. All right, and somehow we're going to manipulate this to be cosine of x. Whole bunch of algebra coming, right? First of all, we need to use a trigonometric identity that you've probably seen in pre-calculus at some point. But sine of x plus h winds up being sine of x cosine of h plus cosine of x sine of h. Well, it looks like we made things more complicated, but actually the fact that we have only x and h in the argument, so to speak, makes things easier. In particular, note that we've got a sine of x here and a sine of x there, so we can go ahead and factor it out. So we're going to have cosine of h minus 1 all over h. And then I guess here I'm going to split the fraction too. So we have a cosine of x and then a sine of h over here, right? So you see we took this guy, put it over here, and then split the fraction with that guy. All right. Now at this point, a little bit tricky here. This, maybe you can see what's going to happen there. Maybe that's going to be clear why that's going to be cosine of x. But this not totally clear. Well, first of all, let's use some limit laws to say that, look, we can take the limit of this, assuming the limit of everything exists, which it's going to, we can take the limit of this guy plus the limit of this guy. All right. Well, thinking about this, in fact, we can even use limit laws a little bit better. Take the sine and the cosine all the way out of the limit, right? So really, we're just worried about these two limits. Right? So we've got this. Well, hopefully we remember at this point that whatever happens with this guy, this is going to be plus cosine of x times 1, right? This is by, was that fact 2? Yeah. Right? This bad boy becomes 1. Right? Let me just highlight it. This guy becomes 1 by fact 2. Very cool, right? Very cool. So there's our cosine of x. So I guess we're hoping that this guy is going to wind up being 0, and it turns out it will. Right? So let's see. We have sine of x times the limit as h approaches 0 of... well, no real way to simplify that, at least looking at it. But we can use that little trickery where we multiply by the conjugate. I know we've never thought of the conjugate of a trig function before. You can do it. Conjugate using trig function totally works. You can use the conjugate of anything. Anyway, this is going to wind up giving us sine of x times this limit, and when you multiply it all out, you get cosine squared of h minus 1 all over h times cosine of h plus 1. And then this is going to be over here separately on the side, cosine of x. How is this going to simplify? Well, it turns out that sine squared plus cosine squared equals 1. Actually, sorry, time out. That's a very fundamentally important identity I need to talk about here. Back here with the unit circle, using the Pythagorean theorem, since the adjacent side is cosine and the opposite side is sine and the hypotenuse is 1, you have this fundamentally important identity, right? A squared plus b squared equals c squared, right? Sine squared of theta plus cosine squared of theta equals 1 squared, or just 1, okay? So if sine squared plus cosine squared equals 1, then we're going to get sine of x times the limit as h approaches, that's an h approaches 0, of that's going to wind up being negative sine squared of h. All right, and for technical purposes, you'll see in a sec, I'm going to divide that into sine of h times sine of h all over h, and then times this mess. Ooh, I'm spilling down there a little bit here. I'm just going to have to go on to the next page here. Told you there's a lot of algebra. Anyway, we're going to wind up getting this equals, right over here, equals sine of x times the limit as h approaches 0 of negative sine of h over h times sine of h over cosine of h plus 1, and then separately plus cosine of x. Okay, now we know that this goes to 1 by fact 2. And this goes to 0. So all of this nonsense winds up equaling cosine of x. Whew. Done. Okay. Now, similarly, the derivative of cosine of x equals negative sine of x. It's a similar sort of proof. Let's not do it here. Okay? Well, if we know that, then we know the derivative of negative sine of x is going to be negative cosine of x. And the derivative of negative cosine of x equals sine of x. Right? So we have this chain, right? sine, and the derivative of that is cosine, the derivative of that is negative sine, the derivative of that is negative cosine, and then the derivative of that, oh, it's sine again. Right, and this is all taking the derivative, taking the derivative, taking the derivative, taking the derivative. So if I said something like, hey, find the 25th derivative of sine of x, well, I guess this is the same thing as saying I guess that's 25 equals 6 times 4 plus 1. So effectively, this is just f prime of x, right? Because every 4 derivatives, we get back to what we started with. All right. So anyway, let's find derivatives of each of the following. Tangent, okay? So the derivative of tangent is the same as the derivative of sine over cosine. Right? Because we don't know anything about tangent, but we do know the derivative of sine, we do know the derivative of cosine, and we do know the quotient rule. So we have low d high minus high d low all over low squared. Well, notice that this kind of makes these things positive, right? And remember that cosine squared plus sine squared equals 1. So this winds up being secant squared of x. What's the derivative of secant of x? Well, I don't know. But I do know the derivative of 1 over cosine of x, right? Which, remember, that's what secant is defined to be. So we wind up getting low d high, remember the derivative of a constant is 0, minus high d low, all over low squared. This winds up being sine over cosine squared. Let's sort of group that a little bit nicer, and we'll have 1 over cosine times sine over cosine, which gives us secant of x, tangent of x. So the derivative of secant is secant tangent. Okay, now that we know trig derivatives, we can also start using product and quotient rules with them, right? So we're going to have this. The derivative with respect to x of this guy equals, well, take the derivative of the square root of x, leave the cosine alone, plus, leave the square root of x alone, and take the derivative of cosine, which is negative sine, so I'll change that plus to a minus and write it like that. Done. And then sometimes you just have some nasty stuff. I don't want to write the d of dx over all that. Well, I guess I will. This is going to equal cosine of x plus sine of x. Leave the second term alone. Plus, leave the first term alone. Take the derivative of the second term. And that's what we've got.